The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Carl Sagan.
Welcome to the Lessons from Nature podcast, modeling the secrets of the bees. Hosted by Mark Rubin.
I'm Mark Rubin, and this is the Lessons from Nature podcast, modeling the secrets of the bees. And today, I'm talking with Chris Farrow. Chris is an astrophysicist who studies the physics of money moving around the planet at large scales. And before that, he studied the physics of weather patterns on the planet. And today we're talking about the idea that light is honey, which means that light is energy, and that energy is used in various ways around the planet, keeping us all alive. Hello, Chris. Good to see you again on episode 2.
Hi, Mark. It's great to be here.
Great. So what I'm going to do now is play the chapter from the book. Secret 2, Light is Honey. The energy in sunlight beams through time and space. Nothing can move faster. Only light can win this race. The sunlight that shines towards us is rich beyond compare. The energy inside this light is like honey we all share. It takes just 8 short minutes for this honey to arrive. When it gleams upon our planet, it keeps all living things alive. Everything that's living moves this energy around. Honey's made of sugar that rises from the ground. Light is all around us. It's plain as day to see. Honey comes from sunlight and sunlight's energy. The energy in sunlight gives it all it's worth. Its lucky light is honey, and it's headed towards the earth. We are talking about the idea that light is honey. And what that means is that the energy in sunlight comes to this planet, is converted into sugar, and the bees convert that sugar energy into stored energy in the form of honey. And before we get into the discussion, what I'd like to do is sort of just read to you a process that I believe is happening. And as a person who studied physics, basically asking you to comment on this as I go through it. My understanding is that light energy is combined with carbon dioxide and water, and that process is called photosynthesis. And that process allows organic chemistry, or enables organic chemistry, to store that solar energy in the form of sugar. Is that right?
Yeah, essentially we're converting electromagnetic radiation into stored chemical energy, is how I might describe it.
Okay,
But
fascinating.
yes, that's right.
And almost all living things that we know of on this planet are powered by this energy. Is that right? Are there any exceptions to this?
Well, I think there's a few exceptions. Examples might be creatures that live at the bottom of the ocean that are they get their energy from thermal vents that spew out sulfur and hot water, and so there's no sunlight that directly reaches them. There may be a few other examples of creatures that, bacteria and so on, that live in caves. But for the most part, if you're looking at sort of the percentage of biomass, then it's virtually all life that's powered by the sun. Yes.
Where does the energy come from for the living things that are not powered directly by sunlight?
So that would be geothermal energy. And geothermal energy itself arises from the residual heat from the planet formation, and some of the elements that are in the center of the Earth are radioactive, and they'll release further heat through nuclear fission. If we think about it, all of that material itself was forged in either a sun during its normal fusion, or if the elements are heavier than iron, then those would have been created during a supernova of a previous generation of stars. And then that material itself will come together to form the Earth. And so the middle of the Earth is very high pressure and very hot. And that's how we get things like plate tectonics and volcanoes. So
As far as we know, then the energy that's powering all living things came from a star in some way.
that's right. It might not be our sun. And again, I think it's important to realize that gravity catalyzes everything. So absolutely the energy is coming from, if it's photonic energy, that's going to be the sun. If it's residual like nuclear fission, then that's going to be the result of a supernova.
So that's really fascinating. And I want to just run you through a series of a process of how I understand our conversation working at a much more sort of tactical level, which is that I believe I'm conscious. Would you agree with that? As an outside observer on the other end of this Zoom, am I a conscious person, do you think? As far as you can tell?
I think to believe you have to be conscious, so
Okay.
it's almost self-referential. But yeah, and consciousness is something that's fascinated me for a long time. It's something that you are, but nobody can really pin it down.
Yeah, I agree. I think it's a fascinating idea. Carl Sagan had a quote about we're a way for the universe to know itself. And we're part of the universe. We're made of stardust powered by sunlight. And we're aware of ourselves and others. And what is that? Like what, but, philosophical, discussion.
I mean, it could be the raison d'etre of the universe in terms of creating beings that can understand what it is. There's also a connection to quantum mechanics. And if we think about nuclear fusion, that's all described by quantum mechanics. There's a role of an observer, and typically in quantum mechanics, and there's lots of interpretations, but you need to have a conscious observer. And so that leads to ideas that all material has some aspect of consciousness. It really is a mind-blowing topic, if you will, but something that certainly has interested me quite a lot.
If it was truly mind-blowing, I wouldn't be conscious. Now, that brings me to the next step in the sequence, which is cognition. Okay. Yep. So in addition to being conscious, my mind is processing information in the form of cognition. And the way that my cognition works is I see things from 6 perspectives, which is who and what am I looking at? How many are there? Where are they? When are they? How did they get there? And why? And my mind puts all those things together into a model that I visualize, and that's how I know what's going on. And I think that's probably true for, I don't know if it's true for anyone else, but like, those are all the things that my mind is answering at all times, okay, of like what is going on. And after cognition, for me, comes thoughts, which is sort of like an intentional way to organize those 6 perspectives into a sequence of things. And I have thoughts. And if I want to convey those thoughts, then what happens is 2 things. I move different parts of my bodies in different ways. One way is body language, like I'm moving my hand, body language. But another form of body language is actual vocal language, which is body language combined with air, okay? Where I'm moving different parts of my mouth and throat and whatever, and I am vibrating the air. And those vibrations are going through this machine over here. You can't see this microphone. And then they're getting converted into electrical signals down over here where my computer is. And then they're being split apart into a zillion packets and like moved around the planet Earth in different ways and through routers and like complex things. And then they're reassembled on your end. Okay. And then they come out through these things on your ears and called headphones. And then they vibrate the air again right near your ears. And those little hairs in your ears vibrate, and it sends an electrical signal to your brain. And that triggers in you first cognition, and then thoughts. And then I'm creating in your mind activity. And then I'm putting my thoughts into your mind by transferring them through this mechanism. And the calories, the energy that it takes me to do this is more than 0, which means every word costs 0.000001 calories. And if you're thinking thoughts as a result of hearing my words, or even if you're not thinking, if you're just hearing them, I'm causing your brain to burn more calories to process that information. The more thoughts I put in your brain, the you're like, what? You're going to lose 2 kilograms by the end of this podcast because what's going on? Because basically the more work, and that's the word, work, the more work your brain has to do to understand something, the more calories it costs. And if you were sleeping, it would cost less unless you were dreaming, and then it would cost more, potentially, depending on what you're dreaming about. And so what we're exchanging is energy and information right now, is that I'm using energy to create information that I'm transmitting through the air, through these mechanisms, and through the internet across vast distances, putting them in your mind. And then you have the opportunity to respond. What do you say to that, Chris? This exchange?
Well, that's quite a process, but I think it's accurate.
Okay.
And it's one of the interesting things about sound waves, as you describe them, is sound waves are pressure waves in the atmosphere, and within our ears we convert those to frequencies, and that's a process called a Fourier transform, which is really taking those pressure waves, converting them to frequency. You'll hear high frequency, low frequency, etc. But then our brains reassemble those impulses where they would be converted, as you correctly described, in the ear into electrical pulses that go into the brain. And amazingly enough, as humans, we all seem to do it the same way. And you touched on a point that I think is correct. Your interpretation of what you see, what you think, is not necessarily the same for me.
Right.
What you see as the color blue, you might see it one way. I would never know what's in your mind. But because we have that power to describe, there's lots of ideas that we can exchange. And I think it's incredibly powerful to be able to have that type of communication.
Now, you mentioned frequencies. I know light also has frequencies. Are our eyes doing a similar Fourier transform with light for us to process colors? Or is that a different process? Do you know?
I think that's a different process. That has more to do with the energy of the light. So the different colors really depend on the wavelength or the frequency. So those two are related by the speed of light. The frequency is the speed of light divided by the wavelength, and vice versa. So I think it's more to do with the energy that's hitting your eyeball. But definitely with the sound wave, it's a pressure wave that then gets converted into a frequency.
I see the difference. Okay, interesting. Yeah, I never knew. And so thanks for, I understand the difference. Thank you for saying that. Now, in this chapter, Light is Honey, I talk about, the idea that this energy that is stored by the bees was originally in the light. And there's an analogy there with, fossil fuels. Can you get me through the process of what's the smallest unit of energy that you know of? It's smaller than an atom, right? There's smaller things than hydrogen. Like what's smaller? Muons? I don't know.
Well, there's something called the Planck length or the Planck time, and that's the smallest distance that you can measure or time that you could measure. And we got to remember from Einstein general relativity that space and time are actually the same thing. We perceive them as different for various reasons, the frame of reference that we're in, and we're not going near the speed of light and so on. But the smallest unit of energy, it's a good question. I've actually never thought about what the smallest quantum of energy could be, because what happens is that, if we think of the wavelength of light, we talked before about ozone protecting us from ultraviolet light. Ultraviolet light is high energy. There's higher energy, there's gamma rays, et cetera, there's X-rays. But as you go down the other way, what's happening is those wavelengths are getting longer and longer. So I guess you could say that the smallest unit of energy would correspond to light having a wavelength that was equal to the size of the universe.
Ooh, fascinating. Okay, well, let's name that something. Let's call that one universaton. Okay, there's one universaton of energy, and then somehow upstream of that, there's a hydrogen atom. So, Chris, how can we get, from a physics perspective, from the smallest unit of energy that you can imagine, whether it has a name or not, to sugar, a sugar molecule? And can you get me to there?
I'll give it a shot. So the first thing we need to do is create fundamental particles out of energy. And there's lots of theories about how the Big Bang came to be and where did that energy come from. And people talk about quantum vibrations in a vacuum and so on. But to get to the fundamental particles, first we can think about an electron. And an electron has a mass. And because of Einstein's special relativity equation, E equals mc squared, we can figure out what the mass of the electron is, and we can relate that to a specific energy. Okay. Now, the proton has a bigger mass, actually a much bigger mass. It's almost 2,000 times more massive than the electron. So it's going to require even more energy. Where does that energy come from? Initially, it came from the Big Bang. Where does that energy come from? Frankly, nobody knows. So I certainly don't know. But that's what you need to do is first start creating fundamental particles. And the most important fundamental particles that we have in the universe, at least when we start to think about the cosmology of the Big Bang, are protons, what we call alpha particles, which are helium nuclei, which really is a group. There's 2 protons and 2 neutrons that form together. And that's also what's going on in the center of the sun is hydrogen is being turned into helium. But that also happened in the Big Bang. And so those alpha particles also require energy, and that energy would be calculable from the mass of the protons and neutrons. And it turns out that the mass of an alpha particle is slightly less than the mass of 2 protons and 2 neutrons. And that energy is released through the process of fusion. Okay. And so then the next thing that has to happen is we have basically a cloud of this gas, which is created in the Big Bang, and it becomes gravitationally unstable, and it starts to contract. And as it contracts, it gets hotter. And as it gets really hot, it starts to create fusion again. So this is not the Big Bang fusion, but fusion that is catalyzed by gravity. And that's what powers the star.
Right.
And as we spoke a little bit about earlier, in order to get a planet, and therefore bees and honey, you're going to need to have heavier elements. And so what goes on in a star, initially, the star is going to take hydrogen and turn that into helium. And that's one process. And eventually runs out of fuel. So it creates most of the hydrogen turns into helium. And then what it does is it starts creating heavier elements. And those helium nuclei, alpha particles, will then fuse together and they'll create predominantly carbon, nitrogen, and oxygen. You can use fusion to create elements really up to iron. Anything heavier than iron really requires the star to go supernova. So what happens there? What happens is the star runs out of the nuclear fuel for carbon, nitrogen, and oxygen, and it has nothing else, no fusion to push back on the gravity. And so gravity starts to win, and it pulls all that material in even tighter. And that's going to hit a process called a white dwarf, where all the electrons, there's something called the Pauli exclusion principle. And so the electrons don't want to get too close together, and that will create a hard bounce. But if the star is big enough, it'll overcome that and keep getting smaller. And then you'll get to the neutrons creating the bounce, and that's going to be called the neutron star. And when it gets to that point, the gravitational energy is pulling the material in very tightly. It hits that neutron star, and it just goes supernova. So it's like a big bounce. And what happens there is, there's a lot of energy released, and that's where we create, or that the star that's going supernova creates the heavier elements. And so not only are the elements lighter than and including iron released, but the heavier elements are released in that process. So then you can create from that material not only another star, because you still have a lot of hydrogen and helium in the universe, but you also have the heavier material, and astronomers will call anything heavier than helium, they'll call those metals. So you have the metals which can create planets. And that's a necessary step in order for life as we know it to evolve. That's what you need to happen in order to create bees. And so then the bees can go and exploit the plants. And we can get into a bit of the evolution of plant life and so on. But we've had 4.5 billion years on the Earth. We started off with something called stromatolites, and the stromatolites were really the first life. They had to be under the water to protect them from the ozone. They started creating oxygen, which went into the atmosphere. Eventually, that created an ozone layer, and then life could start to expand onto the land. Plants started to develop, and then animals would come and they'd eat the plants. The plants were doing the photosynthesis, which was taking the sunlight, the photons, turning that into stored chemical energy in the form of sugars, as you mentioned. And then later, as things evolve, they're going to create flowers, and they need to pollinate in order to reproduce, and they need pollinators. And so they bribe maybe or pay the pollinators through nectar, and then the bees will take the nectar and distill that down into honey. So we might distill things into other things that make it so we can't drive, but the bees will distill nectar down into honey, and that's a form of highly concentrated sugar, as I'm sure you know.
So I'm going to try to summarize what you said, is that there's energy in atomic structures, and I'm going to just start with hydrogen. And depending on the amount of hydrogen, the volume or mass, I suppose, mass of hydrogen in one particular concentration in space, different things happen if you have a big, gigantic cloud of this stuff or a smaller cloud. And imagine there's a cloud of hydrogen that's too small to create a star. And there's probably different clouds that coalesce together because of gravity, like cloud A, cloud B, cloud C, and they make like gigantic, stars. And depending on the mass gravity interaction of the sizes of these things, you have the different phases of star development. And each phase of a star development may either just make things that are lighter than iron or potentially heavier, on the atomic scale, depending on how much pressure, I don't know if that's right, gravitational pressure, I suppose.
Yep.
Is that a thing? Okay, gravitational pressure. Okay, so if you have a gigantic amount, you get more pressure, and then things blow up in different ways at different times, depending on different things. And then the outcome of that are the elements and light. Okay, and then over time, 4.5 billion years or whatever it is, over time, those elements and that energy combine through organic chemistry and interactions between atmospheres, gaseous atmospheres, and light, creating ozone, which can protect us from the harmful rays of light. And also things that live underwater, which also protects them from harmful rays of light in different ways. And all these magical combinations of things occur, and things evolve. And basically things that survive have survivor bias, and then they reproduce in different ways. And that leads to a case where there's plants that are growing. And then eventually some of those plants have this concept called flowers, because somehow it's advantageous to spread their DNA, like somehow this way. And then bees come along because the flowers are marketing to the bees, hey, come here, I have some money for you in the form of sugar. And then they pay the bees in sugar, and the bees bring it back to the hive and process it in a hive. And that's how they're storing the solar energy. And that's how light is honey.
Yeah, I think that's a great description.
Okay, well, it's your description. I just, read some research.
And just to pick up on a couple points that may be interesting, if you consider Jupiter as an example, Jupiter is kind of a failed star.
Oh.
In the sense of it's not massive enough to start the fusion. The other thing that again is maybe not that intuitive, but the larger the star, the shorter the life. Okay, because they get hotter and quick. So that's important because you needed these stars to go supernova. So the universe is about 13 billion years old. The Earth is about 4.5 billion years old. And so you had about 8 billion years roughly to get the supernovas going, have them explode, and then have those heavier elements come together to form a solar system.
So it takes a long time
yes
to cook a universe.
Yeah.
right? To create like the stew of the universe, and different things are happening at different rates. But really, what's governing it, as if I'm hearing you right, is basically the mass of hydrogen in one particular place or spot coordinate system in space. If the hydrogen was just dispersed evenly, okay, then not much would happen. But whatever it is, gravity is sort of pulling it together into creating these objects that then blow up in different ways and create everything else.
That's right. And the explanation for the clumpiness of the universe, if you will, is due to when you had the Big Bang, there's something called inflation. And that inflation captured these little quantum fluctuations where the density was a little bit higher in some areas than in others. But you're absolutely right. If the hydrogen was distributed homogeneously throughout the universe, gravity wouldn't be able to pull it together to form a star, and it would be a very boring universe.
Let's go back to episode 1, secret 1. Life is lucky.
Yeah.
And so whatever combination of things has occurred to enable this, Zoom call to happen,
Yeah.
whatever that was, here we are. That's
Yep, we're here.
I want to add a couple more things about the size of the energy storage. If you think through the idea that energy originated in very, very small things, subatomic things, and then became atomic particles, or hydrogen, for example. And then when it's stored as sugar, the sugar molecule is a lot bigger than a hydrogen atom. And I don't know what the orders of magnitude are, but zillions of, is that a scientific word? Lots of zeros. Okay. Bigger. Let me get my calculator. Anyway, do you know how, with orders of magnitude? Any idea?
Well, I don't think they're that much bigger because, the sugar is a hydrocarbon, right?
Yeah.
So the sugar molecules are made of carbon, hydrogen, etc. And I forget the exact number, but it's sort of below 20.
That's right.
Atoms in the molecule, but hydrogen is definitely a part of that fundamental building block. I think one of the things to keep in mind is that the energy from fusion, which is described by equals mc squared, is much higher than the energy that can be released chemically,
right?
Like by processing sugar.
Yeah, there's losses. There's always losses. There's losses in everything. And I understand why, because but going back to your original today, not all the energy is converted, just the difference in the mass of those two.
That's right. Yeah.
Yeah. Was it the electron shell or some kind of binding energy or something like that?
Yeah, it's more of the nucleus the nuclear binding energy.
You're right. Okay.
Yeah.
So it's not the whole shebang. Because it was the whole shebang, it'd be bad.
Yeah. In the sun, the electrons are separated from the protons. So it's not really the case that you have hydrogen in the middle of the sun. What you have is a plasma that's got a bunch of protons surrounded by effectively an electron gas. And then, of course, you do have the alpha particles that we mentioned. You don't have a proton with an electron going around in the orbit. It's just way too hot at the center of the sun.
It was at some point that, right?
Yes.
Okay. Yeah. And then
before gravity heated it all up.
So the original fuel source was that. And then it gets sort of, stripped away and moved around in different ways because of the heat. Now, an interesting side note, Light is Honey. You mentioned the sugar molecule. Do you know what the shape of the sugar molecule is?
Not offhand.
It's a hexagon. And do you know what shape the bees store it in?
Well, I know that's a hexagon.
Right. And do you know why they're the same?
No, but I would love to hear why that's the case.
Because time is honey, and that's chapter 4. It's the most efficient shape. So there's in that chapter much later in the book, there's a chapter about energy storage. It costs the least amount of work to store the most amount of light. See, the bees have to use energy to create a structure. Okay, because time is honey. Because they have to do work. So they're gathering sugar and converting it into wax to store energy. And triangles are the strongest shape. And when you want to build a three-dimensional structure out of triangles, what do we send into space? Like when we want to send strong light things into space, what's the shape of that, Chris?
I'm going to say
a-
hexagon because you're teeing me up for that, or triangular, but
Yeah, honeycomb. Honeycomb is the shape of things that are man-made, that are strong, that use the least amount of materials. The lightest, strongest shape is a hexagon for the same reason. And so we've converged on, hexagon stuff for the same reason, is that when you do the math and you figure out, if it takes time to gather the resource, what would the geometric shape be that would require the least amount of time, which is the least amount of energy, to be the strongest and hold the biggest volume?
Mhm.
You end up at a hexagon. And guess what? That's why the sugar molecule is the same shape, because nature is always optimizing at the molecular level and at the structural level. And I find that fascinating that the molecule of the hexagon in what my bee project, okay, I'm storing it also.
Oh, nice.
Not metaphorically, like for this reason, okay, in the most efficient shape of a hexagon for the same reason. It's good when patterns repeat. Why mess with a good thing, Chris?
Exactly.
Yeah.
I did learn something about honey since
What?
we last spoke. So I had no idea about this, but I was trying to propagate some basil, and I was going online trying to figure out how to clone it. And it turns out honey is a rooting hormone.
Huh.
And I never knew that. And I can use all the help I can get. So trying to propagate my basil, it turns out if you dip the cutting in honey, it's going to give it a higher probability of rooting.
Interesting.
Now, I have no idea why that's the case.
Must
And
be.
apparently it's only organic honey that does that. So I've bought some organic honey and I'm about to start experimenting.
Chris, in about 2 months, I'll be sending you some organic honey from the hives in my backyard. And you can, as you know, that is payment for being on the podcast. 1 jar of the most inspirational honey in the world is coming your way.
Send me
Okay.
some stored energy. That's awesome.
We'll move it around. Well, Chris, thank you so much again for spending time with me on the Lessons from Nature podcast, Series 1, Modeling the Secrets of the Bees, where we discuss today, light is honey.
It's been a pleasure, Mark. Thank you.